Hello? Okay. Yeah, I'd like to thank the organizers for inviting me to this wonderful workshop. I actually learned a lot during the last 4 or 5 days I was here. And thank you for staying. And I also know it's a challenge to stand between you and the lunch. So I'm counting on Mario to keep me straight. This title was given to me by Bill, from railway lines to Airbus wings. And I think through the talk you will see where this title came about. This is the outline of my talk. My lecture notes didn't quite make into the book, but booklet, but you have a handout in your bag. And I'll be basically talking about from the lecture notes. First, I will briefly introduce to you what is engineering diffraction. And I will show how neutron diffraction, powder diffraction, is used for strain measurements, and more importantly, for neutron, and now with high-energy synchrotron, you can actually do volumetric mapping in large subjects. This is a very important development in the neutron scattering community. That is a measurement standard developed by under the guidance of VAMOS TW20. That is a measurement protocol can be used to tell the industry that we have a reliable measurement methods that can be trusted. And this actually has opened up a great area for industrial application. Now you can actually talk to companies and tell them what has been done. This is in the booklet, in the lecture notes, but because, as I noticed in the audience, not too many are actually in this field yet, so I will actually skip it. And if you like to talk about it, I will be more than happy to tell you about the best some of the practices in this work. Examples, there will be examples littered throughout this talk, but I'll be specifically talking about an in situ study of residual stress and temperature during welding, while a weld is being made. Most of these work are engineering oriented, but nowadays, of course, we know deformation behaviors, fundamental understanding of deformation behaviors is also very important. So I'll be spending some time to tell you about in situ loading studies. And in the end, I will describe some of the new instruments coming along, and along with it, the future research opportunities. And we'll revisit this concept of engineering diffraction. Most of you know this poster. That's the Nobel Prize poster. It was developed in 1994 when the Nobel Prize was awarded to Cliff Shell and Bertram Brockhaus for their pioneering work in neutron scattering, in the development of neutron scattering techniques. But this poster also illustrates where this technique came from. It was mostly developed by physicists, and the initial problems were all condensed matter physics. Here you have a magnetic system. They're looking at a magnetic ordering by Cliff. That was back in the 1950s. And around the late 1950s, Bertram Brockhaus was looking at the lattice dynamics using neutrons. So this trend has continued for quite some time. I think it was not until about in the 70s or late 70s when IIL came along that it really broadened up the user base. And now then you start to see lots of different applications come along. This is a work that was featured in Neutron News back in 1991. By the way, if you haven't subscribed to this magazine, you should. It's free, and it tells you all the development in neutron scattering community. So this was back in 1991. I was a graduate student, and this just opened my eyes to totally different applications of neutron scattering. This work was done at ILL on the old D1A diffractometer by Peter Webster on a piece of railway head. I think this is where the railway lines comes from. And this is the first time that residual stress was mapped in a significant engineering objects. So then you may want to ask, why are we interested in residual stress in mechanical behaviors? Well, basically anything you build, you want it to last. Anything you use, you want it to last, you want it to be low cost, and you want it to be safe. And if you don't do well, there are catastrophic consequences. Of course, I listed these disaster pictures, not to scare you, but just to point it out that, for example, in August of 2007, this twin bridges, this bridge in Twin City in Minnesota collapsed. In '98, this is, most of you are probably familiar with this one. It's an ICE train that crashed in Germany, in northern part of Germany, northwestern part of Germany. And in 2002, there's another there's an airplane that crashed in the strait between Taiwan and mainland China. So all of these things actually can be traced back to some very fundamental damage mechanism. That's a fatigue. This one, the National Transportation Board from the US has determined this crash was due to fatigue in some part of the airplane. And this fatigue behavior was a great concern actually for the US Navies. I believe it's in 2008, the US Navy actually ordered a systematic investigation of fatigue damage in the Navy's air fleet, especially those serviced overseas, because they're worried about fatigue, they're worried about stress corrosion cracking, and so on. We'll get back to this ICE example later. So next, let me just show you how neutrons are used to study mechanical behaviors. Well, it's actually very simple. It's a very simple application of powder diffraction. You shoot neutrons to a sample, and you try to measure the deformation with powder diffraction. Now, looking at one diffraction peak under a stress, this diffraction peak will move to either left or right. So by measuring this peak position, you can determine the average strain within your scattering volume. Of course, diffraction peaks have more information than just peak position. You can also determine the peak width. Under a inhomogeneous stress, the peak will not only shift, but also can broaden. And by analyzing the peak broadening, you can get information on the microstructure, dislocation activities, twin activities, and even phase transition. We have heard talks in the last couple of days on this subject by Matteo and Thomas. And if you analyze the intensity change of the diffraction peak, you can get a sense of the preferred orientation or texture of the material. And we just heard a couple of talks this morning on this subject. So the way you study deformation is really looking at the change, systematic change of a diffraction peak. And stream mapping is a simple application of the penetration capability of neutrons. Here, you take advantage of the fact that neutrons can shoot through a sample by and large. And you use a slit to define an incident beam. And on a reactor source, you use another pair of slits to define a beam for the detector. And the intersection of these two beams gives you this sampling volume. That's a fixed in space. And all you have to do is to move the sample around about this sample position and to get your strain or stress or whatever mapped out. That's how it's defined on a reactor source. As you notice, you only have detectors on one side because of the focusing geometry. With reactors, typically you only use detectors on one side. And that's a schematic. That's a photo of this recently commissioned stress deflectometer at FRM2, the stress-backed. And a time-of-flight neutron deflectometer is a little different. Here, it's actually difficult to, because you have a very large detector array that covering a wide angular, a wide scattering angle. It's hard to use a slit. Here, you actually use radial collimators. But with time of flight, you don't really have this kind of focusing geometry. You can actually use detectors on both sides. So the geometry is slightly different. In the end, the effect is the same. Essentially, you define a scattering volume in real space that is fixed in real space. And you put the sample on a translator, translation stage. To give you some idea of what translation stage looks like, this is the heavy-duty sample table at Vulcan that we just built at SNS. It can support up to 2 tons with a very high precision of 10 micron in movement, and 500 millimeter translation, full degree of rotation. So that Hardy is a pretty tall guy. He's a 6 some feet tall, and it tells you how big the sample table is. And we'll see how useful it is later on. So the initial applications of stream mapping is mostly driven by these industrial problems, as I mentioned before. One of the pioneers in this field is Chalk River by Tom Holden and the company. Here they look at, this is a real industrial component, a gas cylinder used for transporting gas, and it's corroded, and looking at stress and corrosion cracking in this problem. Here we're looking at composite tubes that are used in paper mills. This is a clean tube, but we also look at dirty tubes that have been subjected to operations and corroded and so on and so forth. And the idea is to determine how stress changes with different operating conditions and come up with a solution for the industry. Actually, we did make proposals, and that in the end was implemented. So I was very happy to see that. And if you want to hear more about this story, we can talk later. But one of the most highly visible work or picture is actually this one. This is Engine X that was commissioned in 2003. Soon after that, they put on the huge airplane wings. It was, I believe it was actually Airbus 380 wings. They mounted on this instrument and map out the stress in areas on this wings. Unfortunately, I never heard about, I don't have real data for this work. I don't think it was published. So this came from Airbus. Now, let's get back to this ICE train crash accident. Soon after that, there was a systematic study of the residual stress in the wheel hub of ICE trains. This work was actually done, there's a German train, but the work was actually done at the PSI because at the time, I think FRM2 was not up and running yet. And this was, these plots were given to me by Werner Wagner from PSI. So the equivalent of a National Transportation Board in Germany was looking at what they believe actually the crash was caused by the cracking of this wheel hub after so many years of service. So the idea is to look at the residual strain distribution at different spots in the wheel hub and see how they develop as a function of services. So here shows 3 curves. And the details are not that important, but what's really important are the legends here. This is strain as a function of distance depth below the surface as manufactured after 18 kilometers and after 61 kilometers. And you can see there's a dramatic change in the strain profile. I'm not really sure how, whether these measurements have been related to the fatigue cracking. But you definitely you can see that there is a change, and whether and this change is probably a cause for the fracture of the wheel hub. Now, in order for this technique to be really useful for the industry, you like to be able to hand over to your industrial users a document to say how reliable this technique is. So George Webster of Imperial College took on this challenge back in I think it was 1906 or something like that. And at the time he was at the Imperial College, he was able to organize everybody around the world to do a round-robin study, and from which to develop a measurement protocol. This work was actually done under the auspices of VAMAS. There's an organization for these standards, the Versailles Project on Advanced Materials and Standards. It was a technical area 20. So it was an incredible, as I look back, it was an incredible organizational work because it involves people from several continents. Europe, you got a dozen facilities in Europe participating, all the North American facilities, NIST, Missouri, Lance, Oak Ridge, and Chalk River, and several Asian nuclear neutron scattering laboratories. There's even one from South Africa. So it's about 20 or so facilities measuring the same sample. That's a shrink. Actually, there were 4 samples that were studied in this program. But the most widely studied sample and the only one that actually was documented was this ring and plug shrink fit sample. Basically, you have a ring and you have a plug and you heat them up and then put the plug into the ring and let it cool. During this process, the plug is nailed in the ring, but you also generate a characteristic residual stress field. And that field can be calculated by finite elements, so people know how to do that. And everybody studied the same set of sample. It's a round-robin study, and compare the results. So this figure also shows you that for residual stress measurements, you have to measure at least 3 stress components in order to be able to calculate the stress. And that shows you the orientation geometry with respect to the beam, how this sample is oriented for this hoop, radial, and different strain components. That turned out to be a very successful exercise. This just shows you a measurement as compared to finite element simulations. So how well measurements follow, or to the accuracy of these measurements. There are about 20 set of measurements. The data basically fall on top of each other. So as a result of that, this group was able to produce a document named the neutron diffraction measurements of residual stress in this ring and plug, which has now become a standard document that you can actually talk to your industrial partners. It becomes a protocol for this measurement. And in it, there was also a number of potential pitfalls was identified in making reliable residual stress measurement, such as to make sure that your scattering volume is fully embedded in the sample, and so on and so forth. So this is a very useful document. I believe you can download it from the web. The advances in these neutron scattering measurements has advanced to a stage where you actually can use this method to quantitatively calibrate finite element simulations. This is an example that was actually done in '96, a long time ago, of a simple bead-on-plate weld. Simple weld like this. It's a bead, and that's a 100 millimeter by 100 millimeter weld. And here's a residual strain profile mapped by neutron diffraction with a 2 millimeter spatial resolution. That's finite element calculations. Not only the shapes looks very similar, but you can look at also the magnitude. They're very comparable. And we can actually tell where the finite element fails. For example, here and so on. So these are the things that you can do back in the 1990s and so on. So what's new? What's new is actually to look at things in situ. Here I'm going to show you an example of using neutrons to study friction stir welding while the weld is being made. Now, for those of you who are not very familiar with friction stir welding, this is a so-called solid-state welding joining technique. It actually never involves welding. It's just a you have two work pieces. You plunge in the machine tool essentially, and with a very high speed rotation, and plunge it into the sample and a specimen, and you just drag the specimen along. So in this process, essentially, this tool mix materials from both sides to form a solid joint. This was invented at TWI by, I forgot his name, Thomas. And he patented, I think the patent is still valid for another 20 years, so he will be very rich. This technique initially was developed for high-end applications. So, for example, military airplanes, where you can use friction stir welding instead of rivets. You reduce a lot of weight for the airplanes. But lately, it has been used in commercial products, commercial applications, such as cruise lines, the body for cruise lines, and also for high-speed trains. You weld a large piece, shape them, make whatever the product you need. So one of the fundamental issue with friction stir welding is, again, residual stress. And unfortunately, I don't have a plot for residual stress. That has been done in the early 2000s. You can map out the stress as a function of position across the weld, and you can determine the stress magnitude and see where it reaches peak and so on and so forth. That has been done in 2000s. But what we decided to take a look at is how these residual stress or temperature can develop while you make a weld. So at the time, we brought we don't have neutrons at Oak Ridge, so we contacted our colleagues at Los Alamos and brought our equipment. This is a portable, so-called portable welding machine, but it actually weighs a ton. So we brought that to Los Alamos, mounted it on this SMARTS defectometer, and started to play with it. Now, just to orient you, I'd like to point it out. There are three directions. This is the weld direction. That's the normal to the weld plate. This is a transverse direction, okay? This is the motor that drives the machine tool. I have a little movie. I hope it works. So this is a movie that we recorded while we were making measurements. A lot of people involved, as you will see later. And this is Beyond Clausen. So basically here we plunge the machine tool into this plate, and high-speed spinning, and then you can see the plate is being translated. So during the measurement, the scratching volume is held at the fixed spot relative to the machine tool, and this specimen just moves, okay? And so after that, we can measure the elastic, we can measure the total strain as a function of different positions from the weld tool. So you can imagine you position the scratching volume at different positions away from the weld tool, and we can map out this total strain. Of course, the total strain has two components. One is due to thermal expansion as temperature rises, and the other one is due to elastic strain because of the stress and the mismatch and so on and so forth. So by using a biaxial stress condition that is valid for this thin plate, we're able to separate these out. And so here we actually mapped out how the stress changes as a function of distance from the weld tool, and also at the same time giving you the stress, this is a temperature, sorry, temperature at the same time stress as a function of distance from the weld tool. This value is actually really interesting. That's 350 degrees. It just agrees very well with simulations that was developed for this kind of weld. Now, the other thing you can look at is actually peak width. We haven't really published this work. This was actually done by Chuck Wu, who was this graduate student, in collaboration with Thomas. And you're looking at the peak width at different positions while the weld is being made. And without the raw measurement shows up and down of these peak widths, but if you do proper scaling, taking into account contrast factors, as Thomas does, and you get a beautiful scaling relationship. And this can yield the strain and also particle size for the weld as the weld is being made. You can actually determine the dislocation density at different positions in the weld. This is before, during, and after. So a project like this, of course, involves a lot of people. There's people from Tennessee. Chuck Wu was a student. And there's a group of us and our colleagues at Los Alamos. And John Babb is the guy who made the portable welding machines. And you can see, for the most part, I was just standing around. And now, a lot of these applications in the early stage was driven by these industrial problems, measuring residual stress in welding components and looking at fatigue and so on and so forth. But soon people realized that the stress or strain that you measure cannot really be described by these simple finite element models that only calculates the average stress. So sooner or later, people started looking into what exactly is being measured by neutron diffraction, or X-ray diffraction for that matter. So it turns out there actually is quite complicated. I mean, the stress distribution in the real material is not that simple. It depends on the length scale, how you want to characterize it. Well, if you just look at this schematics that has many grains in there, you can basically characterize the total strain or total stress into three categories. One is this microscopic or average stress, which basically it's a constant across many grains. So let's say it's a constant across the scattering volume that you use. But because within this volume, you have many grains, and each grain has its own orientation. And because the grains are, they have different elastic properties and so on and so forth, this incompatibility creates a partitioning of stress. So in addition to this average stress, you have some fluctuations of strain or stress that varies from grain to grain. So the strain in this grain that with, let's say, 200 parallel to this direction would be different from 200 that was oriented in a different way. If you have a dual phase material, the same would occur. And in addition to that, so this gives a type 2 stress that varies from grain to grain, up and down. But in addition to that, there's also, within each grain, you can also have strain or stress fluctuation. And that gives so-called type 3 stress. This is typically show up in the peak width measurement. So by measuring the peak width, you can try to decipher what's going on or substructure within a grain. But what I'll be concentrating on is the type 2 strain, or so-called intergranular strain, and how you can use neutron diffraction to study the change of these intergranular strain, and from that to gain some insights how materials deform. I have to mention that this intergranular strain actually was recognized long time ago. The first paper that I can find was actually published in 1947 by Greenough from Cambridge using a very simple material, steel. And this is a one-page paper published in Nature where he identified intergranular strain. And 3 years later, he published another paper in Nature as well to basically correct the previous paper. There were some mistakes apparently in the first paper. It was in terms of the magnitude in the strain measurement. But these are back in the 40s and 50s. Now, these intergranular strain measurements basically starts with a load frame. You need to have a load frame to do these in situ loading studies to look at how different grains respond to applied load. This is just a schematic of a load frame mounted on a diffractometer for strain measurements. Here you have detectors, and looking at these two detectors will look at different strains that are parallel to the load direction and transfers to the load direction. I'd like to mention that the literature that you see these days, the bulk of the literature actually comes from these two instruments. One is a SMARTS, the other one is an Nginx, and both are equipped with this uniaxial load frame that has gained a lot of mileage in this field. Essentially, what you're looking at is a plot like this. This is the measured lattice strain for different grains, oriented differently. For different grains, let's say 200, 311, parallel to the loading direction. That is the applied strain. And you can measure how these different grains respond to the applied stress, okay? They're not the same. Unlike what you see in mechanical tests, just load up a curve. Actually, they diverse. The reason they diverse is because the elastic modulus for these different grains, because of elastic anisotropy, they're different. So this initial spread is due to elastic anisotropy. At some point, at about for steel, it's about 200 or 300 megapascal. And you'll see another degree of digression. And for example, for 200, it just becomes flat. It continues to take on stress with the increasing lattice strain. But for other grains, the stress becomes almost, it still goes up a little bit, but it essentially becomes constant. The strain no longer changes. So this is called stress partitioning. It's a stress mostly applied to grains like 200, but very little on things like here is 311, for example. No, not 311, 220. So this means that the grains like 220 is yielding and can no longer carry stress. If you don't have a load frame, you can do similar studies, but ex situ, you load it up, come down, and study the residual intergranular strains for different reflections, and you can get similar answer. It's not quite the same, but you can get similar answers. The way to understand this actually came from a very important modeling by the so-called self-consistent elastic plastic modeling. Mostly it was carried out at Los Alamos by Bjorn Clausen, Carlos Tomei, and the company. And if you want to look into that, just look up these papers from Carlos Tomei. So this is for regular material, stainless steel. Now what happens if you were to study nanomaterials? The example that I showed you is with stainless steel, but for nickel, it's essentially the same because there are FCC, the symmetry, and so on. It's pretty much the same. But what happens if you reduce the grain size to something like 20 nanometers? And that's the material with some different grain size distributions. And so in this case, we actually load up a material to about 3 or 4%, and you can see the material yields at about well, I mean, you actually see 3% plastic strain. And you measure the same thing, okay? In contrast to what you see here, where you have a spread, wide spread after yield, we don't see anything. The lines are essentially straight for all these different reflections. So this essentially tells you one very important simple conclusion, that the nickel grains are not deforming plastically. So then you can start to figure out exactly what's happening. So for coarse grain materials, you have dislocations that's well known, and that gives rise to this intergranular strain. For nanomaterials, apparently this is not developing. And we don't really know exactly what's causing this, but one can imagine, because nickel grains are not deforming plastically, and because the whole material deformed at about 3 or 4% already, that tells you the plastic deformation is in the grain boundaries. So that was a very simple conclusion that you can get by making these intergranular strain measurements. The examples I showed you was monotonic loading, loaded up, come back down, but you can also study this with cyclic loading. You can see how the different components vary, the intergranular strain vary as a function of this tilt angle relative to the loading direction. That can also tell you how the materials, how the damage mechanism, it can tell you about the fatigue damage mechanism in the material. Okay, so far we've been talking about polycrystalline materials where you have these individual peaks. And each peak represents certain lattice spacing from which you can get a characteristic strain. What happened to amorphous materials? Here, you still have some peaks, but these peaks are no longer corresponding to a characteristic distance. I will leave that to you as a question. If you want to talk about it, I'll be happy to discuss with you. Now, in the next few, how many minutes? 1 minute, okay. All right, so in the next 1 minute or so, let me just show you one of the instruments that we built at SNS, this Vulcan defectometer. I'll just use one example to show you how things has evolved. Well, let me just find that. So you've seen this before. This is the instrument hall, experiment room, where you can actually, because of the very large, heavy-duty sample table, you can bring in big equipment. This is one of the things we have. It's a MTS load frame that allows you to do tension, compression, torsion, multi-axial loading, fatigue, everything. With that, you can actually study how the kind of examples I showed you before, but you can also study fatigue and how the different reflections would change during the load cycle. You can also, this is what we're doing now, is trying to implement heating under load, so you can study not only deformation at the room temperature, but also at high temperature, and where the mechanism can be completely different, where diffusional creep kicks in, and so on and so forth. Of course, these are hard experiments, but I was really inspired by this posting just outside this hallway where Patrick Blanket remarked that the real beauty of experiment is to put ideas, actually, to implement ideas rather than put them on a piece of paper. Now, this is another thing that was just implemented, where you can do things very, very rapidly, unlike what you've done before. This is a in situ heating experiment where you put a sample. We will put a sample inside this specialized furnace, and you can heat it at 30 degrees per second. And we heat it up to 1,000 degree, cool it down. You see the phase transition. The whole experiment is done in 5 minutes. Okay, so this is a battery example. Let me just conclude. So I think neutron scattering is really finding increasing applications in material science and engineering for a very simple reason. It's really enabled by this technique of powder diffraction. It's a very simple application of powder diffraction, but it was so powerful. It just opened up new avenues of research. And this field, I also believe the field of engineering diffraction itself is transforming. Now, within the field of engineering diffraction, these time-resolved measurements is really becoming a routine. Sample environment that I showed you before will be a key to implement, and I'd like to have these simultaneous measurement capabilities, and data analysis is always going to be a pain. Thank you very much.
Guys, now it's your turn. Questions? Otherwise, you're not going to eat. Youngsters, come on.
Everything's clear.
Otherwise, Luca is the youngest. Okay.
Oh, maybe not too many engineers. Yeah.
Could be.
Oh, okay. Well, I enjoyed the talk. Yeah, I know a little bit also the work. Actually, I just was why you were surprised about the nickel behavior. Yeah, it's well known that actually, well, what you were measuring was just you were just doing creep deformation, not elastic deformation. And that is very known that when you decrease the crystal size, there are even plots in which they show what is controlling the deformation. So if it is grain boundary sliding or plastic deformation, and that was, there are even for every material, the engineer or there are the plot in which you should know based on temperature, grain size, what you get from.
Yeah, I think there are a lot of different theories as to what is causing the deformation in nanomaterials. But to my knowledge, actually, no one actually was able to pin it down. You look at, there's different simulations from MD, grain boundary sliding, this partial dislocation emission and so on. But has to be careful though. These MD simulations, they're simulated on a different time scale. It's 10 to minus 9, 7, whatever. So my challenge for them is we measure these things. Please come up with a calculation that you can simulate these, or you can calculate this, and let's compare. I agree with you. I mean, many people suspect it's probably the same thing as superplastic materials, as a creep, grain boundary creep, and so on. But that's another interesting thing. How do you calculate the intergranular strain due to grain boundary creep, diffusion? That's something I'd like to see come along. But these are experimental results. We concluded based on, made conclusions based on these experimental results.
I think it's your turn.
Hi, I think
Name?
Giulio Rampronti from Bologna. I think I have, well, I had problems in the past understanding, I think I understood there are different models for functions and shape of the function to separate size and strain. And, well, I'd like to know more about that. Since I just used
experts right here.
I know what the question is quite large. Yeah, and I'm Paul. And I think, well, I always use the Cagliotti for instrumental modeling that assumes that everything from the instrument is Gaussian, and assume that all the Lorentzian part comes from the sample, but just because it's easier for me, and I'm not really interested into size strain. But I'd like to know more about that and all the different models that are there.
Well, I think you have to be careful. These Lorentzian parts not necessarily associated with grain size. As Thomas pointed out, if you have a short-range stress field, you can have a broad, you will have a broad distribution, and more or less like Lorentzian. So I think in order to derive to numbers, parameters from your peak width analysis, you really need to go through the details, not just using it as a black box, and looking at how these, to look at your system and see whether or not these parameters you extract really make sense.
So how do you divide the Lorentzian and Gaussian parts of your pseudo-void? Or you don't use a pseudo-void? I just don't get. Do you fit a pseudo-void on the instrument and say, okay, the instrument has a Gaussian part and a Lorentzian part, and the sample has a Gaussian part and a Lorentzian part?
No, actually, it's more complicated than that because these are time of flight, right? So you have to fold a Gaussian or Lorentzian with the intrinsic pulse shape, and then you deconvolute from that. The way Thomas did is he goes from, he assume a model and then try to fold it with the instrument resolution to match the diffraction pattern.
Mm-hmm.
But in any case, remember that linking strain that you measure with stress that you want to know is the big business. There's another question.
My name is Habibur Chalmers, Gothenburg, Sweden. I have one question about the sample preparation of your technique and versus powder sample. And also, do you use any complementary technique to support your data?
What do you mean sample preparation?
I mean, about you measure the stress of the big things.
Oh,
it is totally different from powder, yeah.
Yeah, I actually, a lot of these experiments are very hard experiments, especially the big, large objects. You really need to think it through before you set it up, because the geometry and so on and so forth can really complicate the measurement. So if that's what you meant by sample preparation, yes. And if possible, you like to use complementary techniques, perhaps high-energy X-ray and so on, to look at different part of it. In fact, especially for these deformation studies, if you use two techniques to bring them together, that can really help you to decipher what's going on. The example that I showed on nanocrystalline nickel, actually this is actually high-energy X-ray data, I have to point it out. We have neutron data shows similar thing. So those two things come together that give you a better answer.
I think if there's no other question, I would like to thank again the speaker of this morning's session. Remember to be back at 2:30 sharp.